It's 12:01, so I'm going to go ahead and get started. Welcome, everyone. My name is John Hagan. I'm chair of this thing called the Maine Climate Table, which I keep emphasizing is different from the Maine Climate Council. This is the fifth Maine Climate Table webinar of 2020. If you don't know anything about the Maine Climate Table, we're a network of organizations, businesses, and individuals interested in basically two things: helping everyone be well informed about timely climate issues like today. And two, we also want to engage, we work really hard at engaging people on climate change across political boundaries and cultural boundaries, because our view is going to take everybody to solve this problem. So go to our website, maineclimatetable.org, if you'd like to learn more. We got lots of interesting things for you there. We're really fortunate to have Dr. Adam Daigneault with us today, doing some fantastic work on pricing natural climate solutions on both agriculture and forestry, although he's just going to talk about the agriculture part today. He'll come back for the forestry part. But before we get started, let me just say a few logistical and housekeeping things. We've all gotten pretty good at Zoom lately. Most of us have anyway. Let me just point out a couple things about Zoom in case you're not used to it. Down at the bottom left of your screen, there's a little microphone and a little video icon, and you can mute yourself or unmute yourself just by clicking on the microphone. Unmute, stop your video, start your video. Same principle. Also at the bottom, most of you again probably know this, there's a participants icon. This registers 51 right now, 52 on my screen. If you click on that, a panel will come up on the right that shows everybody on the call. That's interesting, but the more important thing is at the bottom right of that panel, there's a bunch of little icons, and one of them should be raise a blue, I think it's blue, raise hand button. So if you want to say something, click on that icon, raise hand, and it'll go in the queue, and I'll see that you've got something you want to say, and I'll call on you rather than just jumping in. So raise your hand and I'll call on you in due course. It may be under the more button at the bottom right, but it's there. If you're calling in from a phone, I've never done this, but according to the directions, *6 will mute and unmute your phone, *9 will raise and unraise your hand. I'd ask that you hold your questions until Adam gets through his presentation, because I want to make sure he gets through his presentation. I've learned the hard way, if we ask questions all along, he'll never finish today. So just hang tight. The other thing at the bottom of your screen is a chat icon, little cloud bubble. If you think of a question during the webinar, you can click on the chat, type in your question, and I'll come back to those when Adam's done. So that's an alternative way. Okay, everybody good so far? Any questions? Unmute yourself and ask, otherwise we'll keep going. Hearing, seeing nothing. Okay. All right, so I'm going to take just 2 minutes to queue up this conversation, presentation conversation. In 2017, there was a paper published in the Proceedings of the National Academy of Sciences, a prestigious journal called, the title of the paper was Natural Climate Solutions, and as near as I can tell, that's where the term was coined. It got a lot of attention because this paper quantified globally the potential for natural systems to either capture carbon from the atmosphere or avoid emissions. And before this paper came out, most of the attention was on renewable energy, sort of technological wind and solar energy. But this paper suggested that for relatively low cost, there are a lot of so-called natural climate solutions available to us, such as managing forests for more enduring wood products, or letting forests grow longer, or capturing methane from dairy farms, lots of different things. And the authors calculated in that 2017 2015 paper that 1/3 of the most cost-effective climate mitigation strategies could be achieved through these so-called natural climate solutions. That is, by modifying forestry, agriculture, wetlands management, we could do a lot towards fighting climate change for relatively low cost. Another paper came out in 2018. One of them's on maybe both of them are on our website if you want to read the scientific literature. Another one came out in 2018 that focused just on the US, so downscaled to our country. And while this country level analysis was a good step, if we want to put these practices into work on the ground at the state level or the regional level, we really need a more detailed cost analysis. Adam and I were just talking about that before we started. And that's what Adam is working on for Maine. How much would it cost to actually infuse the soil with biochar in Maine's potato fields? What I like, and I think you all will too, about Adam's work is he puts everything in terms of cost per ton of carbon. And that means you can compare entirely different approaches, such as adding biochar to soil to installing methane digesters on a dairy farm. It's all in the same units of cost. So with this common unit of measure of different land use practices, Adam can even compare various agriculture practices to different forestry practices. And because this common unit of evaluation, it's easier to think through where the state or us as a society might want to place our emphasis in terms of practices, incentives for landowners, for example. If we can get something for $10 a ton of carbon, why pay $100 or $200 per ton of carbon? So it is, Adam's work shows us really this low-hanging fruit. So I'm going to turn it over to Adam. He's doing a project that actually was started in part by the Maine Climate Table 2 years ago, or at least it was wishful thinking. Wolf's Neck Centers joined in, Maine Farmland Trust joined in. Adam's really spearheading the quantification of this work. So Adam, I'm going to turn it over to you. If I'm successful, I'm going to tell us a little bit about your background, how you got interested in this type of work before you start your slide deck. And I'm going to put you on spotlight video. I learned this, which should expand you and minimize everybody else. So Adam, the floor is yours.
Okay, thank you, John. Yeah, so I'm Adam Daigneault. I'm an assistant professor of forest policy and economics at the University of Maine. Sort of just ending up my 4th year here. It's been interesting having to teach online and all that, but I was telling John I got a lot more proficient at Zoom as a result. And just like my students, I hope you guys will chime in if I start sharing slides that are nowhere near what you think should be looking like or whatever. But I think we got this down. I'm a native of Maine, but left when I was 17 to go off to school and really got into took my Maine roots and knowledge and interest in the environment and outdoors and recreation and sort of used that to drive my education, which was a combination of both environmental science and economics. So that really kind of drove my thinking to a lot of approaches to the environment as well. There's always a typically human dimension to it. And sort of the world revolves around money to some degree. So sort of taking that economics lens to help sort of solve the big regional, local, and world problems associated with the environment. I really sort of take that approach. So just like when John asked me to talk today, I said, yeah, this is right up my alley in terms of sort of spreading knowledge and information about how we can go about thinking about these types of issues related to climate mitigation and policy is really looking at it from an economics perspective. John touched upon that this sort of notion of natural climate solutions has sort of came about more recently, primarily with this paper that was led by sort of Nature Conservancy and other collaborators and colleagues. But I've actually been looking at sort of measuring economic costs and benefits of land-based mitigation for the last 15 plus years, initially as part of my PhD, then also working for the US EPA and their climate change office, in between sort of being at EPA and coming back to Maine, I also was basically a policy analyst and a basic consultant for the government in New Zealand, where we focused again on a lot of land-based sort of mitigation practices and costs. For context, New Zealand, about 50% of their entire emissions come from the agricultural sector, so it's a big, big deal comparatively to something like the Maine, which is roughly around 2%. But there, instead of calling it natural climate solutions, we just called it land-based mitigation. So maybe the term itself is relatively new, but people have been studying this from, you could go back to even the late 80s in terms of thinking about incentives for planting trees to sequester carbon and things from that perspective. But yeah, the project itself came about, as John said, got approached at the University of Maine by Maine Climate Table, Maine Farmland Trust, and Wolf's Neck about sort of interest in initially just looking at sort of costs and benefits around soil health, and also sort of different interventions that could come into play in terms of improving soil health and sort of leading to adaptation and mitigation associated with agricultural practices. We've since sort of went down the line to get different sources of funding that are sort of built off of Maine's initiative at the sort of state level to sort of write a new climate action plan, form the Maine Climate Council, and ultimately meet some sort of ambitious climate targets in 2030 and 2015. So that's really what drove sort of what we're talking about today. So, John, I think that's probably enough from that perspective. If we're ready, then I'm happy to go about and just start the presentation.
Okay, you should be able to screen share now.
Okay, that's good. And then the other housekeeping for you, John, is that while you've been talking, I've been admitting more and more people. So the waiting room just continues to get filled. And so you have to keep hitting admit for more to come in. We're all good, but I'm leaving that to you. I can only multitask so much. So
okay, I don't see that button on my screen.
Click Manage Participants, and something should pop up on the side. Right now we're all good, but the waiting room, when you hear those dings.
Okay, well, if they're not here by now, they can't come. So how's that for?
That's fair enough too.
That's better than finding this damn button. Okay.
So all right. So I'm going to share my screen. Hopefully now people are seeing what looks to be a presentation. John's kind of told me stick to a half an hour or less, so we'll see how we go. Those who have heard me talk before know I get quite animated and attempt to stay on task, but when there's such a fascinating topic like this, there's no guarantee. All right, so again, John just basically asked me to talk about putting a price tag on natural climate solutions. As we've touched upon, the overall project that I'm looking at involves both agriculture and forestry. But today I'm just going to talk about the ag side of things, just because sort of the complexities of how, nature runs its course, can make it, I figured it was better just to focus on sort of one sector or one subset. But again, I'm happy to come back and talk more about the forestry aspects as well. So what exactly are natural climate solutions? As John touched upon, it's essentially really defined in that 2017 paper as any action that conserves, restores, or improves the use or management of forests, wetlands, grasslands, and agricultural lands. All right, so that's sort of the management, conservation, restoration side of things, ecosystem management. But really what makes it a climate, quote unquote, solution, right, is really it's also simultaneously increasing carbon storage, all right, or avoiding greenhouse gas emissions. And so some things you can think about that is a focus on protection. So you can protect forests, wetlands, or grasslands, basically from conversion to sort of more emitting sources. You can manage things like timberlands, croplands, and grazing lands better to essentially reduce the amount of emissions that are coming from those lands, or enhance the sequestration from the vegetation that's growing there. Or you can restore land as well, which essentially means, sort of bringing land back to what its natural state was. Sort of, again, that same paper has talked about that globally, natural climate solutions are expected to contribute to at least 20% of the Paris Agreement's aggregate reduction target. So this figure here, I think John talked about, particularly in the early stages, Natural climate solutions are something that can get engaged quite quickly. You don't need a lot of technology. You just need land and willing participants. So therefore, you can get up to maybe potentially sort of 50% in early years in terms of total mitigation. And then as you see, as this wedge gets bigger in terms of where emissions are likely to go absent of any intervention, less the sort of pathway that people are looking for under this Paris Agreement to get 2 degrees Celsius or lower, natural climate solutions can fill in a big part of that wedge, particularly in the sort of first 15 to 20 years of that mitigation process. In the US, so a similar study was undertaken by a lot of the same folks that did the 2017 one, but in 2018, they sort of downscaled it just to the US, and they looked at there was the potential of removing about 21% of the nation's carbon pollution through, again, similar natural climate solutions, which is really equivalent to removing emissions from all cars and trucks on the road and then some. All right, and so this component basically is showing that overall, sort of the biggest mitigation source is coming from forests. About half of that is then through agriculture, and then there's additional contribution through grasslands and coastal habitat. But the key here is that those are sort of really big studies, right? And when you're looking at different sort of geographical scales, the agricultural and land house greenhouse gas emissions can really vary. And so when you think back to sort of IPCC and sort of big global level assessments, they roughly estimate that agriculture and land use through things like deforestation can contribute about 24% of total global emissions. All right, a lot of that is coming from primarily deforestation in developing countries and pastoral agriculture that release a lot of non-CO2 greenhouse gases. In the U.S., the latest emissions calculations from that the EPA released suggested that agriculture is roughly 9% of the total emissions. All right, with most of the emissions coming from transportation and electricity. And then just in this January, the Maine DEP released their latest biennial emissions calculations, and they estimate that agriculture in Maine contributes to just about 2% of total emissions. All right, so much different sort of levels of sort of even magnitude-wise in terms of looking at what agriculture is contributing, right? And so that can also drive sort of the mitigation potential to some degree. Sort of building off of that Maine assessment, so Maine itself has actually seen a 30% drop in agriculture greenhouse gas emissions since 2004, but it's actually also seen a 34% reduction in gross greenhouse gases. All right, so it's basically in terms of both sector-based but overall-based, Maine's definitely on the right trajectory towards reducing emissions, which is essentially a big goal for not just the state of Maine but overall for the world. This figure here is showing sort of where Maine's greenhouse gas emissions have gone since 1990, and I think stops around 2017, 2018. All right, coupled with sort of some recent goals that have come out basically from the administration and legislature at this goal to basically be 80% below 1990 levels in terms of gross greenhouse gas emissions. So these are emissions that are basically being emitted by power plants, transportation, animal-based emissions, fertilizer-based emissions. All right. So right now we're roughly around 18 million metric tons of CO2 equivalent. The goal is to get down below 5 by 2050, which is 80% below 1990. All right, the key here, though, is what this is just talking about gross greenhouse gas emissions, which excludes any sort of forest and ag-based carbon sequestration, which is that idea that basically as vegetation grows, it can deposit or collect carbon in its vegetative stock, as well as deposit that in the soil beneath. All right, so another sort of policy goal that came out that Governor Mills released, I believe last September, was to be 0% net emissions or net zero by 2045. So that's it's sort of another key aspect of what our analysis is looking at, is sort of what is the state of where Maine is in terms of not gross emissions, but sort of net emissions and sort of sequestration side of things. All right, and then what could Maine do to help get to sort of, from this sort of green line down to this red dot, which is really sort of where agriculture, forestry, and sort of other land uses can help fill in that gap. So again, today we're going to talk mostly about agricultural side of things. And so just to sort of tee this up, some agricultural practices that maybe could be considered are things like cover cropping, doing conservation tillage, so not doing sort of intensive tilling year on year, changing crop rotations that basically can do things to promote soil health and enhance carbon in the soil. You could do compost amendments that again help to raise organic matter content and soil organic matter in the soils. On the pasture side, you can think of doing grassland restoration. You could plant legumes that basically add as a sort of an enhancement for livestock grazing. Or you could do sort of grazing optimization, which essentially sort of change the structure of, particularly if you have free range animals, how they sort of roam and range to sort of optimize their consumption while also minimizing sort of damage and inputs on the land. There's other sort of more emerging practices that have come out as of late and are under discussion. The big one being biochar, and that's the idea that you can essentially take pyrolyzed sort of waste and feedstocks, all right, and turn that into a soil additive that it can enhance the organic matter in the soil. I'll touch upon that a little bit more in a bit. So really the key is we can come up with all these practices, right? But really what we want to know is what are the benefits and costs associated with implementing these, and how efficient are the different practices that we might be considering. So the first thing we want to do before we sort of go ahead and start calculating what these impacts might be is we really need to define a baseline or a business as usual pathway, right? And so that's the idea of when we looked at that wedge back with the sort of global NCS figure. It was the one that was going up, up, up. And it's our idea of sort of, if we continue with the current policies and practices, what is the emissions pathway expected to look like? What practices are likely to be implemented? What crops are likely to be grown? All right. And another key thing that we need to gauge is we need to really define the geographical boundary that we're looking to measure these over, as well as the temporal scale. All right. And the temporal scale is not too much of it does not have too much of an effect on the agricultural side, with the exception of it does take time to some degree for soil carbon to start sort of building. On the forestry side, particularly in a state like Maine, where it can take decades upon decades, if not centuries, for trees to sort of grow to maturity, that temporal scale has a really important aspect to it, because it can really affect sort of the level of sequestration that you might be estimating, depending on when you cut off that scale. The second aspect of what you really want to do is establish a list of acceptable or appropriate mitigation practices. All right, and this is kind of the sort of looking at the list, what I did before, is sort of having this debate about what mitigation should be included and what's really feasible for that geographical area and temporal scale that you're looking at. All right, a lot of debates within the sort of land use and natural climate solution type mitigation practice sort of discussion have to do around sort of how well you can measure, monitor, and verify that these practices are being implemented correctly. And as a result, the also risk associated with permanence. So, right, you can do low till or no till practices, but then a farmer can also come in and just till that up sort of the next year, right? And it essentially release most of the carbon that was sequestered under that practice. So it's truly not permanent. Same thing as you can have sort of with forest fires and wind throw and other aspects, you have that risk that the overall practice is not permanent. Another one has to do with additionality, and this is the idea of, some farmers are already implementing some practices like no-till, either because they want to, they find it to be beneficial, or maybe they're getting payments through NRCS or sort of another conservation program, right? And so if you're then, you should, the question is then, should you pay farmers more for doing what they're already doing or not, right? And what you really want if you have a limited budget is to do things that are truly additional. The third aspect is this notion of leakage. And it's the idea that if you sort of, an idea is if you stop cutting trees in Maine, right, there's still a forest product market that basically needs to have wood supplied. So is that just going to basically incentivize people in Quebec, New Brunswick, and New Hampshire to cut more trees earlier? therefore essentially minimizing the sort of total effect in terms of carbon sequestration, because what it is essentially those markets are leaking over to other geographical regions. These are all sort of reasons that people sometimes have against sort of thinking about these natural climate solutions, about them being sort of as viable as doing something like, changing energy production from coal-based or natural gas-based to renewables. All right, so just something to think about. The third stage of what we want to do is we want to estimate the cost and benefits of actually implementing these practices, right? And so this is the cost, right? So how much does it cost to actually do it, and then how effective is it? In this case, we're really looking at reducing greenhouse gases, so that's our sort of key goal. All right, the idea is you want to, again, with limited budget, you want to invest in the practices that can get you the best bang for your buck. That is the most, basically, for your dollar, where can you invest that gets you the highest level of carbon sequestration or reduced greenhouse gases? These sort of estimation approaches are typically done using a suite of models and assumptions. Often there's a mix of economic and biophysical modeling tied to that. As often as we are able to, you want to be empirically based. So you want to actually have, based it on agricultural plots, again, data from the field, right? But itself can be complex due to the nature of the sector, right? Sometimes these experiments could take years and years to develop, right? And so as a result, you tend to then have to supplement it with other types of models. The other kind of thing to sort of touch upon too is that, today I'm going to talk mostly about sort of just estimating these financial costs relative to the greenhouse gas benefit, but you can also identify sort of non-financial barriers of adoption, right? So we can say, in some of these situations, you might have seen cases where it says like, well, if you implement that practice, the farmer can receive $20 per acre in terms of net benefits, right? But there might be other barriers that are limiting what they're doing, right? You have to acknowledge that too, that if there's a lot of technological barriers or capital inputs that are required, there's other aspects that could drive sort of maximizing implementation. All right, so just some ways to think about the costs and benefits that might go along with this. So, let's start with the bad, which is the costs, right? And so some practices might require some capital or equipment to actually implement the practice. Think about a digester, right? You'll need to actually purchase the digester, find a place to put it, construct it, right? You need labor both to sort of start with the practice, in terms of implementation, but you might also need ongoing labor on a year-by-year basis as well. There could be maintenance associated with whatever practices and capital you're putting in place. But the other kind of key aspect to think about is it's not just the sort of the equipment or the people that you might need, it's the opportunity costs as well, right? And so some of these cases, practices you might be imposing might reduce your yields, right? So that's going to affect the overall revenue that you can generate. At the same time, if you're sort of looking to put in sort of riparian buffers or restore some grasslands or something, or set aside some conservation area, right? That's going to reduce your overall farmable area, which can also essentially have an opportunity cost to some degree. On the plus side, some practices and some mix of practices can actually lead to yield improvements, all right? In addition, sort of shifting away from some practices can lead to cost savings, so it's not just on the cost side. Overall, you're going to have reduced greenhouse gases, say if you change away from synthetic fertilizers to more biochar and manure-based soil amendments. Again, if you look at ways to sort of enhancing carbon sequestration either in the soil or the actual sort of above ground biomass, right? Those are benefits you're looking for. And then a lot of times these practices have other environmental co-benefits, things like improved soil health, improved water quality, maybe some other aspects of biodiversity and habitat generation as well, right? So it's not just about the sort of greenhouse gas side of things, it's also these other benefits. So now I'm just going to go through a couple examples to kind of show how this works. So this comes from just sort of a generic example that the World Resources Institute came up with, that looking at sort of what are the potential net costs and benefits of cover cropping lagoons. All right, and this is looking at, these numbers are at least on a dollar per acre per year level. So this study basically said, well, the initial cost of shifting to cover cropping is about $44 per acre. That's essentially the cost for the actual cover crop. All right, but there's a number of benefits too. In the short term, you might have reduced soil erosion because those crops are keeping the soil in place, reduced weed and pest control. You're going to have reduced fertilizer use because of nitrogen fixation, and then you potentially have increased yields associated with that cover crop. All right, so that in itself are basically getting you back to where the net benefit is essentially almost net positive just by accounting for those short-term benefits. All right, in the medium and long term, you might have also improved resilience to drought and enhanced fertility as well as you continue to do this cover crops. So overall, you could actually potentially, in this case, they found that you have net benefits of $43 per acre per year, sort of over the long run, if you account for all these sort of benefits relative to the cost. In special circumstances, you might also get reduced soil compaction and forage sales, which then basically really blow out that the benefits are far outweighing the costs, even without thinking any sort of payment for the greenhouse gases that you're mitigating. And so here the key aspect though is this figure shows detailed costs and benefits, but it doesn't include the mitigation potential. So if you're looking at sort of estimating, well, this about putting in cover crops, right? But you're also want to understand how much is that going to improve carbon sequestration or reduce greenhouse gases, you only have half of the calculation. So what I want to do now is sort of touch upon sort of how we do this for the practices and project I'm doing relative to Maine. All right. So the first thing what you really want to do is, again, is you want to look at the technical and physical potential. The example here is I'm looking at reduced till. And right now, if you base on the US Census, US Ag Census from 2017, the estimate there is that there's about 105,000 acres that are currently under intensive tillage. All right. So the idea is that you could probably take all that and to some degree convert to at least reduced till. All right. So that means you're basically shifting that baseline to this new practice, potentially 105,000. All right. To get the actual mitigation potential, then you need to understand that if you go from intensive to reduced till, you're going to get reduced greenhouse gases or enhanced sequestration. And the literature says that in Maine, that's roughly going to be about 0.16 tons of carbon dioxide equivalent per acre per year. So if you multiply the acres by that tons, all right, you get basically 16,892 tons of CO2 equivalent per acre per year. All right, so for context, Maine has roughly 380 to 400,000 tons of carbon dioxide equivalent per year for the entire ag sector. So this number itself is quite low. All right, so that's the mitigation side of things, right? But you want to also understand what's the economic cost of doing so. So from this perspective, you can again take the amount of area that you're going to implement the practice on, 105,000 acres. The mean net revenue from sort of converting different crops to reduced till is roughly $19 per acre per year. All right, so you got a total cost. You divide that then by the amount of mitigation that we estimated, which is 16,892 tons of CO2, and that gets you then what this sort of mean cost per ton, which is the sort of cost dollars per ton of CO2 equivalent, is really the metric that sort of economic analyses and financial comparisons, that's how they're done in the sort of climate change policy world. And so that comes up with $112 per ton CO2 equivalent. All right. And so then you can use that to sort of gauge to other practices. All right. The other thing I'm just talking upon is that this assumes that everyone implements that, all 105,000 acres, all right, and it's a mean person, it's a sort of an average farmer, right? It ignores these other barriers to adaptation, things like perceived risk of doing that, of shifting to reduced till, the technical knowledge that's allowed to do that, and then also farm system compatibility, right? So we're assuming that every single farm can do that. That might not actually be the what's actual the actual numbers they're compatible for. All right, and so that gets us essentially, that's not covered today, but there's another part of our project that we're looking at there. This figure here then is essentially goes through and does that same type of sort of structure of analysis for a number of different practices. And this is the TNC's 2018 study for the US. And what you can do now is that you can do those practices and look under different crops, different geographical areas, and you can build out essentially how much mitigation could happen, all right, under different sort of price points. And so the darker the green it gets essentially means the more costly it is to do so, right? And so under their estimates, sort of in the US, the sort of biggest mitigation potential comes from avoided grassland conversion, cover crops, and biochar. All right, but the key here is that they estimate that cover crops are likely to be the cheapest, all right, because that's low cost in terms of the light green. So that paper is suggesting that really cover crops maybe could be the low-hanging fruit that farmers could go towards and policy could target. But the question we have is that, well, what about Maine, right? That's a national level analysis. Most of these studies that I've touched upon are global and national scale, but there's these state level estimates that are often reliant on assumptions that are more applicable elsewhere. You can't just take a study out of Iowa and assume that that's going to be the same for a typical Maine farmer, right? And then also just acknowledging that there's specific implementation barriers as well. So what we've done here is sort of build off of some of that work that's done in the past, but do it directly applicable to Maine. All right, and so this agriculture greenhouse gas sort of NCS methodology is the following. The approaches we're looking at both the financial and agronomic response analysis. So what are the costs? What are the financial benefits? But also what are the sort of yield benefits or changes as a result? Geography, we're essentially looking at the current major crop area and dairy farms across Maine. This gets us to roughly 400,000 acres. So if you look at sort of ag census, it says that Maine has somewhere near 1.2, 1.3 million acres of farmland. A lot of that farmland is actually in trees, right, or other things that aren't actually farmed. All right, so we decided to focus on sort of the major crops. The time span is looking over 20 years, starting with 2017 to 2037. 2017 is the latest data we have. The baseline is looking at this current practice distribution and emissions by crop that again are based mostly on the census. And we're looking at a number of different opportunities, including cover crops, reduced and no-till, biochar and manure amendments to soil, diversifying rotations, and also basically doing set-asides, which is essentially sort of restoration or conversion of cropland to perennial conserved land. And on the mitigation side, we have a number of emission factors that were basically sourced from the literature. Just to get an idea of where we are on the baseline, so the major crops that we were talking about are on the left. So we looked at potato, low bush blueberry, hay, silage corn, wheat and barley, apples, and then also other vegetables. All right, and then these are essentially the practices where this isn't the total amount of area at all, but the ones who are currently doing some of these practices that we've assumed. All right, and the key is that a lot of cover crops are being implemented in Maine, particularly when it comes to potatoes associated with their rotation practices. Then you can look at, okay, well, if everyone implemented, what might that area be? And you can look at, again, that this is sort of looking at the technical potential in the way that I sort of talked about the different types of tillage practices that we discussed earlier, right? So this is the full implementation, less what's actually also being done. All right, and so by far, we think that some sort of soil amendment is the largest, all right, because that can be done on both hay and cropland. But the key here also is that many practices are not additive, all right? So you're probably not going to do biochar amendment and amend with manure, right? Because they're both sort of targeting the same thing. So that's another aspect to think about sort of how we're going into these numbers. But at least it's sort of establishing what's the technical potential that we can go with before then trying to dig more into the sort of economic side of things. This figure here is showing that sort of where emissions factors are happening in terms of mitigation practices by NCS, right? So the way you can read this bar is the farther the bar goes to the right, all right, the higher mitigation potential that practice has on a per acre basis, all right? So this is another way to look at sort of, it's not just about potential in terms of the amount of acres, but also what's the potential if you implement that relative to the status quo, all right, how much sort of reduction you're actually going to get. What we're showing here is that a biochar amendment is estimated to get you the most mitigation in terms of up to 1.6 tons of carbon dioxide equivalent per acre per year. All right, where things like shifting from reduced till to no till are not going to get you that much, while intensive till to reduced till are getting you a bit more from that perspective. Cover crops, if you focus on legumes versus non-legumes, are again getting more. But in a lot of cases, you're not getting any more than sort of 20 to basically 200 to 300, well, 400 to 600 pounds, I guess, because this is in terms of tons, right? So that's again showing that there's not literally tons and tons of mitigation potential. The other thing is that a lot of analysis you might have seen, they sort of stop here. They take these emissions factors and multiply by the area, and they say, okay, here's the potential, right? But they don't actually account for the economic costs and benefits. So in my picture is only sort of half. All right. So what I want to do, sort of with the last bit of the presentation, is to dig into a bit more about how you actually do this for some of the crops. So the first thing we want to look at is no-till cropping, which is essentially the practice of growing crops without disturbing the soil through tillage. All right, and the benefits are that it increases soil organic matter and improves soil health. All right, its eligibility is mostly for corn and other grains and some vegetables, but not potatoes. So it limits the sort of area that potentially this can be done. All right, the practice is to implement no-till planting on basically all eligible areas. And the sort of literature suggests that the mitigation is somewhere between 0.36 and 0.79 tons of carbon dioxide equivalent per acre per year. Literature also suggests that there's really no noticeable yield change, and in some cases it could actually be negative for some crops. All right, and the input cost for doing no-till is about $22 per acre. So if you take the $22 per acre and then you sort of look at the mitigation potential, and this is a mean cost as well, you get basically that the break-even price, or that sort of mitigation cost, is between $7 and $112 per ton carbon dioxide equivalent per year. All right, with sort of the average getting higher, closer to that $112. The next is biochar amendment, which is essentially a soil amendment that's produced from biomass, where you use pyrolysis technology to essentially char it, where oxygen is either absent or depleted. So it's really dense, sort of dense biomass, where you can then till that into the soil. All right. And as a result, it increases soil carbon, improves soil health. And we've assumed that it's eligible for all crops, pasture, perennials, low bush blueberry, sort of everyone could potentially do this. And what we've done is taken a sort of, again, a mean approach to the literature, where they said you could apply maybe 5.9 tons per acre, and till that in annually for the first couple of years, and then let it do its magic. As I touched upon, its mitigation is about 1.6 tons. The literature is pretty spread out in terms of what the yield change itself is. So we're assuming right now sort of none. You can look at different studies and say some it has negative, some it has positive, but on average it has minimal amount. And the costs are both for the biochar stock itself, but also the transport and application of that stock. And so as a result, if you account for that, all right, it gets a break-even carbon price of about $51 per ton. The third one I'm going to talk about is crop and grassland conversion. And this is the idea that you remove land that is marginal or maybe sensitive areas from actual production. All right, and you converted that into essentially some sort of perennial crop, or trees. All right, it's eligible for potatoes, other vegetables, corn, and other grains. We didn't assume that you would do that with hay fields. The practice is essentially you set aside land, often through an enrollment in some sort of rental program. So you can think about the analogous to something like parts of the conservation reserve program. Mitigation itself is found to be between 1.3 and 2.3 tons of carbon dioxide equivalent per acre per year, mostly in that sort of growing biomass. There's no yield change in this sense because what you're doing is essentially taking crops out of production. All right, and the cost itself is basically the cost of taking that crop out of production. So CRP rental rates basically get at that to some degree. That's roughly about $18 to $47 per acre per year, depending on whether it's grassland or cropland. But then you also have to plant those perennials, which can cost an upfront cost of $376 per acre, which gets you a break-even price of $33 to $45 per ton. All right, so we're getting lower to more to that medium cost range for this case. And the last one I want to talk about has to do with constructing large anaerobic digesters for dairy manure, which basically provides for a biological treatment of manure and other agricultural byproducts by essentially trapping the manure within the digester, which you can see in the background here, and converting that into essentially into biogas. The practice itself is to build a digester that can roughly suit 700 cows, could potentially handle waste from multiple farms. In itself, basically 5.2 tons of carbon dioxide equivalent, mostly in the form of methane per cow per year. It's also got co-benefits of selling biogas, biological gas that are produced and improved water quality. If you break out the sort of capital costs and sort of annualize them over the life of the digester, it roughly comes out to $143 per cow per year, all right, which then is equivalent to about $27 per ton of carbon dioxide equivalent. in terms of mitigation. Sort of taking all that and sort of putting it together with some of the other practices I talked about. Here you can see again, as you go left to right, biochar amendment is likely to have the largest mitigation potential, followed by anaerobic digesters and converting to perennials. All right. These are the ones at the top, including reduced and no-till. All right. Not that much mitigation potential because there's just not that much eligibility, and the actual sort of efficiency is relatively low. The other thing is these costs are actually quite high. So if you look at the actual sort of large mitigation potential ones, they're also the ones that have the sort of lowest cost, often can get massive uptake of these different practices. You could potentially do that on relative cheap amount, so under $50 or less. If you try to sort of additively come up ones that could be additive, you could get anywhere between 0.3 and 0.9 million tons carbon dioxide per year, or a total cost of 8 to 45 million. To put that into context, again, total emissions in Maine are 18 million tons carbon dioxide per year, and agriculture is just 400,000 tons. All right, so we've roughly found that the mitigation potential, all right, particularly with even implementing just one of these practices that's found to sort of be the more cost-effective side, could get you pretty close to being sort of carbon neutral within the agricultural sector. That being said, just focusing on agriculture is not going to get us anywhere near that sort of net zero 2045 goal, mostly just because there's just not that much land in agriculture in Maine. All right, the net zero goal says that if you reduce emissions by 80%, you're still roughly need to fill that gap with about 7 million metric tons of carbon dioxide equivalent. And so here that's sort of showing where that gap still lies. But still really good news from agriculture from that perspective. It can be done if you're looking to have sector by sector sort of carbon neutrality. Just to summarize sort of the big options that we had and the break-even price. So the top three are biochar, large anaerobic digesters, and conversion of marginal cropland to perennials. Those are all either between $27 and 51 tons per carbon dioxide equivalent. Many of the crops that were limited by area and extent and or low greenhouse gas benefits, those are all the ones that I showed at the top here. The other thing is to note that, as John talked about, we have done sort of forest and analogous study on forestry as well. And we found that in forestry, the costs were around $11 to $22 per carbon dioxide equivalent. So on the ag side, the costs are typically more expensive, really falling in that range of $27 to more than 100 plus, if you count some of those sort of no-till and cover cropping type ones that we found. But the good news is that, they're still well within range of, if you compare that to sort of electric-based mitigation, renewals, transport, $50 or less is really a good target. So they're definitely sort of cost competitive from that perspective. And finally, the sector could really potentially be carbon neutral if enough farmers adopt these solutions. All right, but again, they could be costly to achieve without financial and technical assistance. Right, so that's why we measure things in these tons per dollars per ton carbon dioxide equivalent. This really allows us to understand what's the break-even price, what incentives do we have to provide to farmers and landowners to sort of implement this, and or do we have to go above and beyond that because some of these practices, like putting in anaerobic digesters, are also sort of costly from the upfront capital requirements. That's basically what I have. I just want to acknowledge that a lot of this funding came through the U.S. Climate Alliance, as well as Maine Farmland Trust, and a grant that we also got from the Mitchell Center for Sustainability Solutions, for which I'm also a faculty fellow. The forestry side also came through things like Forest Service, NSF, and NASA. And I'll leave it at that. I went over for a few minutes, John, but hopefully I cut off some of the questions that are going to come up anyway. And I thank you guys all for your time, and welcome to hear any questions or comments.
All right, thank you, Adam. I hope you can all hear me again. And it's John Hagan. If you've got a question, if you could raise your hand, I know you must have questions. Click on participants, bottom right panel. There should be a raise hand button. And if you click on that, I will call on you. And I had one or two come in on the chat, so I'll get to that too. Let's see, the hand just disappeared that went up and I lost it. There it is, Scott. Scott, go ahead, unmute and Ask away.
Yeah, hi. This is Scott Flunn out at the Center for an Ecology-Based Economy in Norway. Um, excuse me. This topic is something that I have spent a lot of time looking at, especially both the impacts on agriculture and the potential for agriculture to mitigate climate. And one of the things I study permaculture, and some of the things you mentioned were non-additive. I was wondering about that, like how you could combine cover cropping with biochar, other practices with grazing practices, biochar and grazing practices. Also wondering if you've done any looking at silvopasture, or combining trees with grazing, forest farming, using things like perennial crops like hazelnuts that can sequester carbon, also have grazing integrated in, some more integrated systems, and see if you can kind of shift that cost down and benefit up.
Yeah, Scott, those are both great questions. So start with the first one, right? So I said that not all of them are additive, but that sort of, let me step back. So this project itself was really, we spent a year getting it all together, but the actual analysis, the analytical part was really only kicked off in December. So this is the first start of what's sort of a year long to try to get at sort of honing in on these numbers. All right, so both of your questions tie right back to that. So the first thing is, the next sort of phase is to explore how additive some of these can be, and whether or not you can essentially bundle some of the practices. So some of the work I did, particularly in New Zealand, has been around thinking about that. So that's perfect way to guide, is that yeah, I did misspeak and say that they're not all additive. There's definitely ones that you can do biochar with you can amend the biochar and then do no-till on top of that, or you can think about pasture sort of optimization with that as well. The second question is about silvopasture, and yes, we have started looking into that. And so because it's a bit more complicated than just saying stop tilling the soil, we don't have sort of results yet ready to share, but in the next phase, we're hoping to dig in that a bit more. So I might follow up with you to see if you got some good sources and even anecdotal stuff that can assist with that. That's fantastic. Thank you.
Okay, thanks, Adam. Other questions? Hands can raise hands. If not, I'm going to read, while you're all thinking, I'm going to read some of these chat. Adam, can you see the chat too?
Yes.
Okay, yep. I'm going back to the top.
Okay.
One of the from Bill to everyone regarding grazing, rotational grazing. Do you see that one in the queue? 1224.
Okay, from Bill?
Yeah.
Okay. Okay, regarding grazing, is rotational grazing still in vogue, and is it an environmentally sound way to approach grazing? So the sum, yes. So rotational grazing, it depends. So if I talk to my colleagues in like Rick Kirksberg in Humane Extension, he'll very much tell you it's sort of, it depends on where you are and how you do it. So there's some studies that have come out that say, basically move away, like depending on where you are, move more towards, keep them in the barn and just grow the crop and feed them. Others say that rotational grazing can be done. Again, it's more intensive than in terms of knowledge and technical know-how to get it right, but it definitely can be. It can still be proven to be an environmentally sound approach. It's not all the literature is saying that we should just move all livestock to CAFOs or anything like that.
Next one is on nitrogen consumption in the soil when biochar is introduced.
Right. Okay. So Judy and others, if you start asking about the details of particularly biochar, I'm not going to be the one to give you all the nuts and bolts. There's pros and cons associated with sort of how it can affect the soil. The limitation with this is that there's still not that many studies out there to sort of highlight what those all are. My colleague on this project and others, Ivan Fernandez, is actually looking at doing some trials right now to get at some of these questions about how the soil composition is indeed being changed in terms of nitrogen consumption and other aspects of that. So sort of stay tuned. Right now, the answer sort of is pretty much it depends. There's no sort of one one answer of yes, it definitely does this or definitely does that. It seems to be a very sort of complex issue, which is probably why, despite a lot of studies, even now mine saying like, go ahead and do biochar, is not being implemented more widely. I think there's a lot more variability around what that mean number says, associated with a lot of sort of the complexities with that. Okay,
All right.
so next one is just Jody says, can we share the slide deck? So that
Yep.
goes to you, John. I think we're going to record and share everything.
Yep, the slide deck and the recording will be posted on our website, probably by tomorrow. And then
Yep, and
in
happy to share.
perpetuity.
And then Jody, again, I spoke with the NWL group a couple months ago. Happy to come and come back and speak again to that group. It's obviously easier now that it's virtually as well, but happy to talk more if necessary. Okay, the next one is, would manure or other materials be delivered to a new digester, and if so, whether greenhouse gas emissions be included here? Well, this is a great question. This comes to the aspect of, if you have a large digester sort of say, on one farm, but it's sort of centrally located in the sense that you need to have multiple farms sort of come and deposit their manure there. How do you account for the fact that are emissions associated with collecting the manure and then transporting and driving it? I believe the studies that we've relied on have actually touched upon that. So this is sort of in the greenhouse gas world, this is where you'd call more the life cycle emissions. So you're not just looking at the one aspect of the manure in the digester, but what's the life cycle of having to, basically go out on the tractor or whatever, or at the dairy shed to collect the manure, transport it and pump it, right? And so from what I've seen, those numbers are still relatively small compared to the whole process, the amount that it mitigates, but it's still not zero. Right. And so that's another thing that we can touch upon basically in the next iteration is talking about that a little bit more, about how that varies along different aspects of the supply chain or life cycle.
Yeah. Andy Whitman asks about conduct analysis on the practices of reducing nitrogen emissions.
So nitrous oxide. So it's a bit implicit in when I talk about sort of reduced CO2 equivalent. So some of the practices that talk about like amendments have a bit associated, like, so you do a manure amendment, right? And so what that is actually what it's primarily doing. It's not just sort of enhancing soil carbon, but it's reducing fertilizer inputs. And so those fertilizer inputs basically are then the nitrogen itself basically converts to nitrous oxide and is emitted that way. So instead of talking specifically about methane or nitrous oxide, I've just coupled that all into this, what we call tons of carbon dioxide equivalent. But again, as we go forward with the study, we can break that out into the different gases and to get a better idea of sort of the relative components associated with that.
I'll get to the webinar on forest in a minute, Adam.
Yep.
I'm going to ask a question now, and we're running out of time if we stop at 1 o'clock. I was thinking that the higher priced practices wouldn't be smart, but it looks like the higher priced ones may deliver more bang for more bang, but also cost more buck. Have you thought, I know you're doing the analysis, but what about converting this to policy ideas? Can you just say a little bit about that, even though I know it's not your responsibility?
Well, it is what it is. I mean, I am a policy professor at UMaine, so I have to.
Okay,
I have to at least try to sound like I know what I'm talking about. There. But,
Good.
Right. Yeah. So exactly that. So using this dollars per ton of CO2 equivalent is just one metric, right? That is economic efficiency, and that's it, right? There's also political feasibility that has to do with some of these practices. And the other aspect too is that we can talk about things like convert to perennial, right? But if you convert all the cropland in Maine to perennial, that's basically potentially wiping out a whole sector, right?
Mm-hmm.
And so it doesn't look at this, also doesn't look at the flow-on effects of that, right? That you suddenly don't have any crops grown, you don't have farmers market, you don't have local food security, et cetera, right? So something like that could be one way to maybe put a damper on reaching maximum potential there. Doing things like cover crops and reduced tillage are not just about enhancing carbon sequestration. The other soil health benefits, right? And they have other aspects that can deal with sort of lifestyle of farming as well to some degree, right? That might dominate sort of the discussion more than just pure sort of carbon politics or climate change being the main factor driving why someone might, or climate change mitigation might being the main factor for driving this. So with that, the idea here is we can at least use these numbers to inform the discussion, but by no means is economics the gospel to say you must do that, right? There's a lot of other nuances that sort of tie into that. The key is to just at least acknowledge that maybe this perception, if you go back and look at the Fargione et al. Study that said, well, the best bang for the buck in the US appears to be cover crops, all right? But in Maine, maybe that's not going to be the case, right? So you need to just think a bit about more before you start diving into promoting that as a practice.
That's well put. There is a political and a socialization element to all of this, but we still need the math, which is what you've done here to just even open the conversation. If you all, it's like a minute or two after 1. If you need to go, go ahead and go. Thank you for joining us today. I will say that if Adam's willing, we will do another one just on forestry. Adam, I'm putting you on the spot here, but
yeah, no, I'm more than happy to.
Yes,
again, for me, it's a two-way street. So I can get this information out to you guys, but again, the only way that this stuff can be utilized and improved is that this gets out to the public, and I get input from each and every one of the people that listen in on what's useful, what's not, how it can be improved. So I think really forestry will help tell the other side of the story, if not more.
Yeah.
Got a lot more area in that.
And it was just too much to try to cram into one webinar on one day. So the forestry piece too, because I know Adam's done a lot of analysis of that. So we'll schedule that, and if you're in our database, you'll hear about it in advance, or just go to our website and see when it'll be scheduled. But we'll try to do that in the next month or so, if Adam's available. So I'm not seeing any other questions or hands in this little after time. So Adam, thank you very much for taking time to do this today and put it together. And if you got questions for Adam, I'll put his email on our website. Everybody knows how to reach Adam pretty much, but put his email, and I'm sure he'd be happy to answer further questions since he wants feedback.
Certainly, and thank you, John, for hosting, and thanks to all you guys for taking time out of your busy day to listen in.
Again, look at our website for the slide deck and the recording, maybe tomorrow. Okay, signing off, everybody. Thank you.